Welcome to Unit 30. We look at statistics. So the plan is to look first at moments. We have already seen probability distribution, cumulative distribution function. Now we have another notion, which is moments. Second, we look at central moments and especially the variance. And so special cases will be the variance, the skewness, and the kurtosis. So that's the plan. I want to keep that short. And at the very end, I want to say something about how you get from data, how you get to the PDF. That's a very important step. We will talk more about data later in this application weeks. So the first thing we are doing is moments. Let me just introduce moments. So if f is a probability distribution function, so what we do is we define mk, which is the integral from minus infinity to infinity, x to the k f of x dx. So this is the kth moment. And I just want to remind you about a couple of things. The first moment, actually let's start at the zeroth moment. m0 is then, this is equal to 1. So that's just the minus infinity to infinity 1 f of x dx. Because that's always 1, that's not interesting. But the m1 is already interesting because we have already introduced this f of x dx. That is what we call the mean. It's also denoted by mu, sometimes it's the mean. And so on. So m2 also plays an important role. That's the second moment, x square fx dx. So these are moments. And it's actually interesting that these moments, and you know all these moments, you can reconstruct the probability distribution function. So they are useful because they are just numbers. And the next thing I want to do is I want to introduce the central moments. So that was second part, the central moments, when we have the integral from minus infinity to infinity, and then we take x minus m, where m is the mean, to the k fx dx. That's called the kth central moment. It's very important, and we usually denote them by mu k. So mu is the Greek m, and so you just say mu. So that's the central moment, and very important is the mu2. The mu2 is the integral from minus infinity to infinity x minus m square f of x dx. Now that's called the variance. The variance of f, variance of the data. And we can foil this out. Let me just show you that about that's part 2 about the central moments. We will look at special cases. A very special case is that's 3. That's the variance. Variance is very, very important. And we look at the variance, that's the mu2. F, we have seen that already. That's the integral from minus infinity to infinity x minus m square fx dx. Now we can FOIL this out, and we see that this is minus infinity to infinity x square f of x dx minus 2 times the integral from minus infinity to infinity x times fx dx, and then plus the integral from minus infinity to infinity m square f of x dx. Now you can simplify that a little bit. So we have in this case, let me just make that like this. This is what we called m2. That's the second moment. That was the first moment, right? That was the m1, and that's just m. That's the mean. This is also, we can take the m out, right? If we take that m out, we get just m square. So that whole thing also is m square. So this is m1 square, which is m square. And so we see that the variance has this nice formula. Mu2 is actually just m2 minus m1 square. So it can be expressed using using just the second moment and the first moment. So that's kind of a useful formula. So that's the variance, and very important in relation to the variance is the sigma, which is the square root of the variance. That's called the standard deviation. Certainly have heard about this. It's a very important notion. It kind of tells you how far, how much the distribution kind of deviates from the mean. If this is large, it means that the distribution is widespread. If it is small, this means everything is concentrated near the mean. So that's a very important notion. And then we can also, with this notion, we can define standardized central moments. What we have is that we just take minus infinity to infinity, and then we take x minus m to the k, and we divide just by sigma, so that the standard deviation is equal to 1 f of x dx. And this can be just expressed as mu k over sigma k. So that's kind of a sigma to the power k. So that's kind of a nice formula. So if you know the central moments and if you know the standard deviation, we can get that. And so you see kind of a couple of examples. The standardized second moment is not very interesting. What we have is, actually we call this ck. Let me just write that down. So we call this ck, standardized central moments. That's an official notation. So if you have c2, for example, so that's the c2, that's the mu2 over sigma to the 2, and that's just the variance divided by the variance. So that's always equal to 1. So that's not very interesting. But the third one is actually quite interesting. The third one is mu3 over sigma to the 3. This is called the skewness. This kind of measures how much the distribution is somehow tilted. And so it's kind of the first really interesting case of this standardized central moments. And so that's an interesting notion. And then there's the fourth one, which also appears often, which is the mu4 over sigma to the 4. And that's the kurtosis. Kind of tells you somehow how big the tails are of the distribution. But that's essentially just what I wanted to introduce in this lecture. But we will also in class then do some computations like let me just have a little bit of computations, like if you take the distribution, which is just the exponential distribution. That's kind of an interesting case, e to the minus 6 here and 0 here. So that's the exponential distribution. And in this case we can compute everything very nicely. And so what we have is the mean, which is m1, that's equal to 1, and the variance, which is m2, or m2, let's just look at m2. m2 is equal to 2, but m2 minus m1 squared, that's the variance, that actually is also equal to 1 in this case. We can also compute the other things. The skewness, if you compute it, you get 2, and we will compute that in class hopefully. And then the kurtosis is turns out to be 9. So often one takes the excess kurtosis and subtracts 3. So in this case you see for example in tables you see the excess kurtosis tabled and not the kurtosis. So the last thing I wanted to include in this lecture is a very important point. How do you get from data? So that's extremely important, because data are just numbers. So I can give you some numbers, some random numbers, and I want to know what the distribution function is. So what I'm doing, I'm taking and maybe explain it here with graphics. I can put some graphics here, please. And what we see, so I take some data and I shuffle them, and whenever I have the data in some of the bins, I put more weights there. It's like grades, right? A grade distribution of a test. So what you do is you just look how many cases are here, how many cases are here, how many cases are here. These are bins. And when you do that and you make that fine enough, you kind of see that you get finer and finer bins, and then in the end what you will get, if you get the smoothed out function. This is the smoothed histogram. So these are some names we will see. So there is a histogram, and then there is a smooth histogram, and if properly scaled, this is the PDF. So that's how you start. You start with data, you get to the histogram, then you produce a smooth histogram, and from the smooth histogram you can get then the PDF. That's extremely important because you measure something. For example, you measure, you know, how large these markers are, and you will see they are all essentially the same length, but they vary a tiny bit, and the variation of all these lengths will in the end give a distribution. It's usually a normal distribution. Everything is that the mean is the length which you expect. It's also called the expectation value, and then you have some deviations. Some of the markers are a little bit larger than the others, tiny bit. So in this case you don't see it even by eye, the difference. But that's how you get, if you measure things and you get you write down the data, you produce the data, you get to a distribution function, which is then your model. And with this model you analyze the data. So you can compute all kind of properties from this data, like these quantities which we have just introduced: mean, variance, standard deviation, skewness, kurtosis, or other higher moments. And that's often very useful for understanding the data. And that's it for today. So let's just see.